Hello again, students. Now we're going to talk about section 2 of chapter 20, electrostatics. So for section 2, our essential questions are: how does the electrostatic force depend on the distance between two charged objects? How can you charge objects by conduction and induction? And what is Coulomb's law and how is it used? So our vocabulary, again, you can also reference the virtual word wall that I've posted in this module on Canvas. To review, we remember that force means a push or pull, that it's a mutual force between two objects, that it can be attractive or repulsive. And our new vocabulary words are electroscope, charging by conduction, charging by induction, grounding, Coulomb's law, Coulomb, and elementary charge. The electrostatic force can be determined by suspending a charged rod so that it turns easily. The results of experiments and actions of the charged rods can be summarized the following way. There are two kinds of electric charges, positive and negative. Charges exert forces on other charges at a distance. So this is a non-contact or field force. The force is stronger when the charges are closer together and weaker when they're further apart. Like charges repel and opposite charges attract. So we're talking about a charged rod, for example, and let me see if I can show you my camera. This is what we will come to know as an electroscope, but I can charge two objects. There's a little delay in my video camera recorder, but so here I have, I'm sorry, it's very close up, but this is a stick of PVC, the black plastic stick, and a piece of, unfortunately, rabbit fur. But if I rub them together, I can charge, so I'm transferring charges as I rub them together from the fur to the plastic, leaving the plastic charged with one type of charge and the fur charged with the opposite type of charge, if we follow our idea of conservation of charge. And then if you look closely, you can see that as I move the stick close to the fur, it might look like the fur is moving because the stick is brushing it, but it's actually moving because there's charge on the stick and opposite charge on the fur. In any case, we'll look more closely at this phenomenon in some of the kitchen physics, but this is upcoming. Back to the lecture. So we can determine from charged rods. So for example, maybe I charged the PVC one way and I charged, say, a piece of glass another way. And I could tell that they were different types of charge because they attract or because they repel. And if I have one rod suspended so that it can easily move, that's how I can determine whether they attract or repel. So an electroscope, that's one of your vocabulary words, consists of a metal knob connected by a metal stem to two thin, lightweight pieces of foil called leaves. This is an electroscope made from a beaker, and we do have electroscopes like this in the classroom. However, this is not the kind of electroscope I grabbed when I had the chance to get back to the classroom. Instead, you saw a brief picture of the electroscope I did get from the classroom. It's a slightly different configuration, but it does the same thing. So first I will describe it and then I'll show you our version of electroscope. So electroscopes are sensitive and useful for determining electric charge. The picture on the right shows a neutral electroscope. So when an electroscope is neutral, the leaves hang loosely and they're enclosed in this glass container to eliminate air currents, right? They're really thin aluminum, that's just pieces of aluminum foil. And a moving air current can disturb the leaves and make it look like they're moving due to charge rather than air. In any case, the type of charge carried by an electroscope can be determined by observing the leaves when a rod of known charge is brought. So if you happen to know that the PVC pipe, piece of pipe is charged negatively, then you know that the leaves separate because of negative charge. So how it works. Let's see, we want to go to this video. Nope, that's not what we want to go to. Okay, in any case, I'll continue to describe and then I will show you our version. So there are several ways to charge a neutral object. We can charge a neutral body by touching it with a charged body, as shown to the right, and that's called charging by conduction. When a negatively charged rod is touched to the knob of an electroscope, electrons are added to the electroscope. The electrons, of course, are repelling each other. They're mutually repulsive because they're same charge, so they spread out through the conductor. They spread out evenly through the knob, down through the rod to the leaves. The leaves are now same negatively charged, and so they repel each other. They spread apart. The process of charging a neutral object by bringing a charged object nearby but not touching is called charging by induction. The process then of removing excess charge by connecting an object to Earth is called grounding, and we'll see those processes in examples coming up. But first, let me show you our version of electroscope. And like I said, there's a delay, something to do with the screencasting. There's a delay between my camera and the recording. I'm trying to convince the camera to, there we go. Okay, so here's our version of the electroscope. So you can see at the top, there's a top circular plate. This is made of aluminum. That aluminum is connected through conductive nuts and bolts down to a holder. So this straight, well, actually it's not straight, it's a zigzaggedy piece of aluminum inside. It's all electrically connected or conductively connected to the top disc. Then in the inside on that stick of aluminum, that zigzag of aluminum, is suspended. It's basically a straw. It's like a paper straw that is itself covered in aluminum. So everything here is conductive through from the top disc to the inside stem. And then you'll see this piece of white plastic that's kind of between the top stem and the bottom. And now my camera's trying to I'm waiting for it to decide where it wants to focus, refocus. We're having technical difficulties. I will totally love, if you know about cameras, to know what you think is going on. I wonder if I can force it to. Let's see, focus. Come on, you turkey. Oh, I see the button here. She's a confused camera who's very delayed. Oh, that did not help me at all. Ha! Camera. We don't have time for this. Okay, but in any case, we're looking at a situation where we have conductive stuff, metal stuff, going through. And if I bring a charged object close to the top, I'm again waiting for, there you go. She's slow. I even have it on the very lowest resolution setting. Okay, so again, I have the PVC rod and a piece of bunny fur, and I'm going to rub the PVC rod with the bunny fur, and in doing so, I'm transferring electrons from the fur to the rod. We'll learn more about that later in kitchen physics. But if I then bring the charged rod close to the top of the electroscope, and there's a very annoying delay as I'm trying to show you and explain. I'll hold myself still while the video catches up. But you'll see that as I hold that charged rod, I'm not touching it. If I hold it next to the electroscope, the needle in the electroscope deflects from the main sort of vein, right? The needle being the movable aluminum covered straw deflects. And if I bring the rod closer, you'll see that the deflection is larger. And if I pull the rod away, you'll see that the deflection becomes less. So that's showing how the charges get pushed more. So the force is bigger with closer proximity. Then if I touch my charged rod to the top disc, I'm transferring extra charge from the rod to the hole of the inside of the electroscope. And now I can take the rod away, and I've deposited extra electrons now into the electroscope. Those extra electrons have mutually repelled each other throughout the conductor and arranged themselves trying to get as far away from each other as they can. And now the electroscope itself holds extra negative charge, and I can sort of measure some relative amount of extra charge by the angle of deflection of the needle. So that's our version of an electroscope, and we'll keep talking about it, and I'll show you bits and pieces of it as we use it in our kitchen physics coming up. Okay, so let me show you a video of the same, or almost the same situation. It takes me a moment to navigate the mess that is.
Suppose that a negatively charged rod is brought close to one of two identical insulated metal spheres that are touching. Electrons from the first sphere will be forced onto the sphere farther from the rod and will make it negatively charged. The closer sphere is now positively charged. If the spheres are separated while the rod is nearby, each sphere will have a charge, and the charges will be equal but opposite. This process of charging an object without touching it is called charging by induction. A single object can be charged by induction through grounding. Grounding is the process of connecting a body to Earth to eliminate excess charge. Earth is a very large sphere, and it can absorb great amounts of charge without becoming noticeably charged itself. If a charged body is touched to Earth, almost any amount of charge can flow to Earth. If a negatively charged rod is brought close to the knob of an electroscope, electrons are repelled onto the leaves. If the knob is then grounded on the side opposite the charged rod, electrons will be pushed from the electroscope into the ground until the leaves are neutral. Removing the ground before the rod leaves the electroscope with a deficit of electrons, and it will be positively charged.
Okay, we have lots more to practice with charging by induction and contact, but that's the basic idea. The type of charge carried by an electroscope can be determined by observing the leaves when a rod of known charge is brought close to the knob. So I know that the black PVC plastic stick gained a negative charge from the fur based on the chemistry of the fur molecules versus the PVC molecules, to be explained later. And so I've charged my electroscope negatively. I have an excess negative charge on the main vein and the movable dial, let's call it, the movable straw. So if I then bring a negatively charged object near it, I should see even further deflection, right? I'm pushing even more negative stuff down into the bottom. And if I bring a positively charged thing nearby, I should see electrons, I should see the effect of electrons, the extra electrons down there in the electroscope being drawn up, being attracted to the positively charged rod. So I should see the leaves fall. I should see them get closer together. So the leaves will spread farther apart if the rod and the electroscope have the same charge. The leaves will fall slightly if the electroscope's charge is opposite that of the rod. And I think all of this will be clearer when we see it in real life in kitchen physics. I'm going to skip this animation, and instead we'll just define Coulomb's law. So Charles Coulomb in, I think it was 1700s, but I can correct myself later in kitchen physics if my date's wrong, played around with charged objects and discovered that the amount of charge changed the amount of force, and the distance between the two charged objects changed the amount of force. And not just those qualitative descriptions, but he collected enough evidence to fit that to an equation model. So according to Coulomb's law, the magnitude of the force between 2 point charges, and point charges, we just mean things that are real small, so that we don't have to worry about how their shape or size affects the force between them. So the magnitude of the force between two charged particles, QA and QB, at distance r apart, can be written as follows. So the force is equal to K, a constant, times the amount of charge on object A, times the amount of charge on object B, divided by the distance between those two objects squared. So amount of charge matters, but distance almost matters more because it's squared. The electric force, like all other forces, is a vector quantity. Force vectors need a magnitude and a direction. However, that equation above really only gives the magnitude of the force, the amount of force. To determine direction, you need to draw a diagram and interpret the charge relations carefully. Are they both the same charge? Repulsive. Are they opposite charges? Attractive. Coulomb's law is valid only for point charges or for uniform spherical charge distributions. It gets much more complicated if they're blobs of weird shape or extended objects. The SI standard unit of charge is called a coulomb, capital C. 1 coulomb of charge is about the charge of 6.24 times 10 to the 18th electrons or protons. So a coulomb is a very large unit of charge compared to a single electron or proton's charge. Another way to say the same thing is that the charge on a single electron is only 1.60 times 10 to the negative 19th coulombs, a very tiny amount of charge. The sign for that charge is negative versus the sign for the proton's charge is positive. The magnitude of the charge of an electron is called the elementary charge. We now understand that electrons are leptons. They're, as far as we know, fundamental particles. They can't get any smaller. They're not made up of smaller stuff. And they have this certain amount of charge. So we call the charge of the electron itself a fundamental elementary particle, elementary charge. We now know, of course, that protons have the same charge as an electron, right? They have equal but opposite signed charges. We know that protons themselves are made of quarks and that quarks have partial chunks of electrons worth of charge, but we still call the amount of charge on an electron the elementary charge. The magnitude of the charge of the proton is equal to the magnitude of the charge of an electron, but they're exactly opposite types of charge. There are many applications of electric forces on particles. They're used to collect soot and smokestacks, trying to reduce air pollution. Tiny paint droplets charged by induction can be used to paint automobiles and other objects very uniformly. Photocopy machines use static electricity to place black toner on a page so that a precise reproduction of the original document is made. Same story with laser printers, I think. Just kidding, that's not correct, but we'll come back to that. In other instances, applications are designed to avoid the buildup of static charge and to safely eliminate any charge that does build up. For example, static charge can ruin film if it attracts dust, and electronic equipment can be damaged by discharge of static charge. People who work on electronics often have to worry about whether they are grounded and how any charge that they accumulate might affect touching a sensitive chip in an electronic device. So, review of the essential questions. Have we addressed these? How does the electrostatic force depend on the distance between charges? We're starting to understand. How can you charge an object by conduction and induction? Lots to learn still. It will help a lot to see it in real life, but my camera is too delayed for me to show you now, so we'll do kitchen physics next. What is Coulomb's law and how is it used? You've seen the equation. We have some practice to do as well with that. But this lecture is meant as an introduction. You should now have complete lecture notes for Chapter 20 for electrostatics. You can go back through the video and re-watch if you've missed something. You're going to either do that by hand, you're either going to have printed out the PDF and handwritten in the notes, or you have been typing in the fields as you take the notes. Save that PDF and then upload it to Canvas. I'll see you next time for some kitchen physics.